able to control the system. So first we must have an analysis of the system that we have, okay, and then we must be able to design a system, a control part, such that from this control part we will be able to manipulate the system. So what is system analysis? Study of the behavior of the system which involves assessment about its stability and performance. Okay, so our body is a system, isn't it? Everything we see in the universe is a system. The solar, the celestial bodies including the sun is what is called the solar system. Solar system again forms a small part of another large system, isn't it? So you can break systems into minor levels, or you can build systems into major levels. Now we must have all the basic, we must study about all the basic behaviors of the system. So the study of the behavior of the system which involves assessment of its stability and performance. So we must know about the stability and the performance of the system. So how can this be done? This can be done by mathematically modeling the system, because we are going to deal it mathematical way. Okay. Every physical system we are going to model it into a mathematical system. So this can be done by mathematically modeling the system. Now how can you design a control system? By control part of the system, the design of control law or control signal is so that overall system becomes stable and offers the desired performance. So what is the target of controlling the system? The target of controlling the system is that the system has to be made stable. And the second one, it should offer what? It should offer the desired performance. So basically we have a system. We must know an assessment about its stability and performance. And this will be done by mathematical modeling. And then we are going to design the control part. And what is the aim of designing the control part? Aim of designing the control part is to make the system stable and to keep the system within the desired performance range. So the system should give you the desired performance output. Now for the purpose of analysis and control design, a system may be represented equivalently in either time domain or frequency domain. So we are going to define mathematical modeling areas. Okay. Now how can you define a system? You can define a system, number one, you can define it in the time domain with respect to t. Here the time domain, our variable is t, which is the time, and you can also design it with respect to, model it with respect to frequency, which is what is called frequency domain. So what are the dependent quantities of the system? The number one dependent quantity of the system is time, and the number two dependent quantity of the system is frequency. Okay. The discussion here is limited to linear systems, because it is practically very difficult to model non-linear systems. Non-linear system design we will deal when we are going to come into the end of the chapter with a state variable approach. So primarily at the starting of the subject, our discussion is limited to what? Our discussion is limited to discussion of linear systems with the constant parameters. So that means the parameters are not varying. So such systems can be conveniently represented using number one, differential equations, number two, transfer functions, and number three, state space representation. Okay, so which are the ways, which are the domains in which we can model a system? We can domain a system, we can model a system in the time domain with respect to the variable t, or we can do it in the frequency domain with respect to variable f. Now, mathematically, the systems can be modeled by using number one, differential equations, number two, transfer functions which involve Laplace transform, and number three, which involve state space representation including matrices. Okay, so these are the areas, or these are the tools by which a system can be modeled and designed. Now what about differential equation? Differential equation, you all know that it involves d by dt and its integral form. Okay, so it can be d by dt, or it can be d square t by dt square, and then it can be the integral form also. Okay, so this is we are modeling it with respect to an ordinary differential equation. Okay, so every kind of a system, if it is time variant or time invariant, linear, non-linear, etc. can be represented in terms of differential equation. So differential equation gives you a provision to define a system as a mathematical model, even if the system is a time variant system, time invariant system, linear system, or non-linear system. For example, let us consider an RLC circuit. If this is R, this is L, and this is C. So I am drawing an RLC series circuit. Okay, this is an RLC series circuit with an R value, with a resistance value, inductance and capacitance. Okay, now if we are applying an voltage V of t across its terminals, and if a current I of t is flowing in the circuit, we are representing it with respect to, we are going to represent it with respect to a differential equation. So it is given with respect to time. So what is our voltage? It is V of t, which is a dependent quantity on time, and there is a current I of t which also depends on time t. Now which are the elements? Our elements are R, L and C. And you see, if C becomes an integral quantity, so what I am going to do is that I am going to avoid C for the time being. We will go with R and L. Okay, so this is R and L. This is a circuit which is an RL circuit. So R is a constant quantity, so it becomes Ri of t. Inductance is a differential quantity, so inductance becomes L di by dt. So it is L di of t by dt is equal to V of t, isn't it? So by Kirchhoff's current law, what will be voltage applied? Voltage applied will be the drop across resistance plus the drop across inductance. So if this is value V1 and this is value V2, what is V1 of t? If this is V1 of t and this is V2 of t, what is V of t? V of t is equal to, V of t is equal to what? It is V1 of t plus V2 of t. It is V1 of t plus V2 of t. And what is V1 of t? V1 of t is the voltage drop which across resistance created by I of t, and V2 of t is the voltage drop across inductance created by the current I of t. So a circuit which is a series circuit, which is an RL circuit, which consists of a resistance and inductance, can be modeled as a differential equation in this format. So once you model this, once you make this equation, then there is no relevance for this circuit. So you can replace this circuit completely with respect to this equation, because you know which are the elements, which are the parameters working in the circuit. So this is how converting a system into its mathematical model. So what was our system? Our system actually was a circuit involving a resistance, inductance, V of t and I of t. But now we have replaced the system. Now there is no need of the physical electrical system, but now we have a mathematical expression which is a differential equation. So when you have this differential equation, then you, for the analysis, you don't need the system. So the circuit can be avoided. This can be also done with respect to a transfer function. So the first method was converting a system into its differential equation. Now the second method is converting the system into its transfer function. When you say transfer function is actually the Laplace transform of output divided by input. It is the Laplace transform of output by the input. So this question can come as a part A question for your UG program, because what is defined transfer function. A 2 mark, 3 mark or a 4 mark question can come for your UG. So you have to remember this slide, make note about this slide and reproduce it for your UG program. You will get the full marks for the part A question. So what is a transfer function? Transfer function of a system is the Laplace transform of its input impulse response, that is ratio of the Laplace transform of the output signal to the Laplace transform of the input signal. So it is ratio of Laplace transform of the output signal to the Laplace transform of the input signal. So what is our output? Our output is Y, and what is our input excitation? Our input excitation is R. So what is Laplace transform of the output? It is Y of S, and what is Laplace transform of the excitation input? It is R of S. So what is our transfer function? Our transfer function is G of S, which is Y of S divided by R of S. Now what is the initial condition? Our initial conditions are 0. Very, very important. Our initial conditions are 0. We have to assume 0 initial conditions. So that means there is no internal initial stored energy in the system. The entire energy stored in the system when we are going to start analyzing the system is 0. So that means there is no initial internal energy stored in the system. That is what we mean by 0 initial condition. So when the circuit is in 0 initial condition and you have an output corresponding to an input, and your output is Y, input is R, and you take the Laplace transform of the output to make it Y of S and the Laplace transform of input to make it R of